Okay, second part of looking at the light from stars, and this one is a little bit harder, but it's data sheet questions that you've got. So equations coming in here from your book. Okay, so keep your book handy. That makes it work so much better. So I showed you this last year. I showed you this when we did quantum in the videos during lockdown, and the idea is that as you get things hotter, okay, as you change their temperature, well, they look different colours. So the PHET website is really good for this. Play with the star colours, black body radiation. So a perfect black body, something that gives out all wavelengths of light. Again, all the way down from the really long infrared through the red up to the higher and higher frequencies, the shorter wavelengths down here. Basically, wavelength, the peak visible wavelength, is what changes with temperature in our main viewing. Okay, so to us, if we just look at the light, we will see different colours. Something that's around about 7,000 degrees will look bluish. If you get something at 7,000 Kelvin, at 6,000 Kelvin is starting to look kind of greeny blue, maybe a bit more white. We are getting yellow when you're down at 5,000 Kelvin. You're getting more into the red, dark red, infrared at 4,000, etc., etc. So different colours of stars to the visible eye look different colours because of this black body peak on the what's known as the Wine distribution or Vine distribution. Okay, so it's the black body radiation thing itself. Now, mathematically, okay, there is an equation in it. However, it's just a way of estimating. So notice that. So how does it work? It's basically, and it's worth saying, they say the maximum wavelength in the data sheet, so warning here, is proportional to 1 over temperature. Okay, this is not the highest wavelength, okay, along here, sorry, highest wavelength along here, because this actually goes on forever. It fades out smaller and smaller. This is actually the peak wavelength. So be wary in the exams, this is the peak wavelength, okay, where most light is seen and therefore the most obvious colour when you look at it. So be wary of that phrase. Now, you can be asked to compare stars using this. So again, just go back to your basic way of doing things with proportion. If you multiply by t, it's going to equal a constant. Okay, so if you need to work out a new temperature of a different star because it's got a different colour wavelength or vice versa, find out your first star's temperature and wavelength, work out the constant, and then divide it back to find the missing value for the second star. Okay, so fairly straightforward. But yeah, it doesn't get to an equal sign on any of that. It keeps it very vague. Now, adding to that, okay, and this is where it gets complicated. We're then starting to put several things together. You move on from Wien's law and you get Stefan's law. Okay, now Stefan's law, or to be precise, it says Stefan Boltzmann, he of the gases and so on, so all that study of energy, show the relationship between temperature and luminosity. Okay, now luminosity is defined as energy emitted per second, which if you think about it is power. Okay, so we can talk about the luminosity. It's the visual light power that comes from the sun or other stars, sorry. So in this one we have L equals 4 pi r squared times by rho, okay, which is a constant, times by the temperature to the power of 4. So it's known as Stefan's fourth law. not because he had 3 others, but because it's temperature to the power of 4. So what we see in terms of the brightness, okay, the actual brightness given out depends on the surface area of the star, yeah, which we'll come up to and bring up. But it depends on a constant, which is given for you again on your data sheet, I think. Let me just double check, because I've suddenly thought maybe it's not. So on my dirty sheet here, yes we do. So we have the Stefan constant on the bottom of your data sheet. Okay. So given to you, watts per meter squared per Kelvin to the -4. So you can always, if you're ever asked for the equation, you can work it around. But again, let's just have a look on our data sheet, and you'll find that the mathematics of them is basically not in here. Okay, sorry, I'm looking at cosmology, astrophysics. So in the astrophysics section, you've got that thing. So the Wien's and the Stefan's law. Okay, so what we'll often do is pick up on the meaning of this, and they'll break it down a little bit. So L is luminosity, and that's going to be in watts. Okay. R is the radius of the star, or, this is more important, displacement. Excuse me, ambulance shoots past. Displacement from the star. Okay. In proper units, meters. Okay, because we have meters down here. And T is the temperature. Temp of star in Kelvin. Oh, excuse me, I don't know why I put in. So Kelvin. Now, that gives them interesting things. Basically, it tells us a couple of things in particular. So, luminosity, excuse me, I'll get it under the camera. Luminosity is proportional to fourth power of temperature. Okay, so L is proportional to T to the power of 4. So in a standard star, if we go all the way back to that Hertzsprung-Russell diagram, there should be a link in between these. Okay, but it gets a bit more complicated because of the process that's going on inside the star. But there is a link. The second thing, it's basically is proportional to surface area. Of a sphere. Okay, now this doesn't have to be the surface area of the star itself. If you get further away, the luminosity, the brightness, is going to get less. Okay, the power is being spread out over a larger area. Do we all remember the butter gun? Yeah, this is the area of the whole sphere, not just the actual size of butter at the beginning. Okay, so this links in with the idea of intensity, and it's slightly different due to the other definitions, other part of this definition. But yeah, it's the area of a bubble of butter being spread outwards. So as we get further and further away, we start to get less and less light entering our telescope, entering our eyes, and so on. So we get less power, less energy every second. Sphere radiating outwards. Excuse me, radiating outwards from the star. So don't just think it's about the size of the star itself. Okay, it's more than that. It's a useful tool to work out how luminous something is. Where does it come together? It does mean that if they have links with the star, then we can get it, but as it says here, if two stars have the same temperature, the larger one will be brighter, it'll be more luminous, it will give us more power. Okay, but you can use it to estimate the radius of a star, but you can also use it to do other things as well. So from what we were saying last year, it links in with the idea of intensity. Just remember that the idea of intensity was a basically slightly different effect. How intense something looks is not the same as its luminosity. Luminosity is just power, whereas intensity is the idea of concentration of power, brightness per meter squared. Okay, so basically, just going to put in brackets after this, intensity was power per meter squared. Okay, so it does link in with that. As I said last year, we had the intensity is, given out is just whatever the original energy was per second. So energy emitted over time, original energy. Okay, this isn't how we had it last year, we just said I naught. But basically, if we multiply that by 4 pi r squared, then what we'll get is basically the brightness at any point within the sky. But again, it was all that idea of proportionality. Okay, so there could be a k in here. Basically, the whole idea was intensity multiplied by 4 pi r squared equals a constant. So again, convenient reminder from last year, because actually it's quite easy to work about how the intensity changes with distance. It's the same as what we got over here. Okay, so just a simplified version of the Stefan's law. There is an analogy between the two. So in your questions, they are quite often asking you to link luminosity with that idea of Wien's law, wavelength from the intensity and the temperature. Okay, so wavelength really from the temperature, but that then links us to, the temperature links us to not just the wavelength, but also the intensity itself. Okay, so worth putting back on here that this is your Stefan's fourth law, I think, because that links to go Stefan's fourth law depends on the temperature, which depends on the wavelength. So they're all interlinked. You can't have one without the other. Okay, so questions tend to have those broken into steps, but they'll ask you to join them. And again, proportional. It's a really helpful way of doing it. That is proportional to. Yeah, so you got to kind of keep thinking like that. It makes it much, much easier. I suppose for correctness, we should say L is proportional to A. There we go. Covers all angles then. Brilliant. Okay, that's quite a hard bit, I think. Not necessarily from an idea, but for the mathematics, you need to practice some questions. So we'll do that in the lesson.